Here in chapter 2.2, we are studying the properties of matrix operations. Our objectives for this chapter are to know and use the properties that are associated with the matrix operations of addition, subtraction, scalar multiplication, and matrix multiplication that we saw in the last section, and then the properties associated with the zero and identity matrices. We are going to know which properties of fields do not hold for matrices and which properties of fields do hold for matrices. And we are also going to learn in the next set of videos how to find the transpose of a matrix and know the properties of the transpose. The real numbers, which we indicate here with the bold R, together with the operations addition and multiplication, is an example of a mathematical field. So notice subtraction and division aren't included. The complex numbers, which we denote with bold C, again with addition and multiplication, is another example of a mathematical field. As you study higher levels of mathematics, you'll come into contact with more fields and their operations. So fields and their operations have all of these usual properties that we're familiar with from the real numbers. The first property here is closure. So if you have two elements, A and B, in the real numbers, then their sum, A plus B, is also in the real numbers. Addition is associative, so depending on how we group it, whether we add A plus B first, as on the left, or B plus C first, as on the right, when we do our addition, we still get the same results. So regardless of grouping, addition meets the associative properties. Addition is commutative, so we can add in either order. We can say A plus B or B plus A and still get the same results. In addition, we have an additive identity, 0. So 0 is in the real numbers, and it has a property that any number A for default here, plus 0 gives us back the result A for any number A in the real numbers. Additive inverses, what we think of as opposites, also exists. So for every number A in R, it has an opposite negative A, such that A plus negative A gives us 0. So we call this the opposite sign or the additive inverse. And we actually define subtraction as A plus the additive inverse of B. So you could think about subtraction that way. Closure under multiplication. So if you've got A and B, both elements or numbers in the real numbers, then the product is also in the real numbers. And multiplication is also associative. Regardless of how we group the multiplication, we get the same result. So whether you multiply AB first, as on the left, or you multiply BC first, as on the right, we get the same product for both of these sides of the equality here in part 7. Multiplication is also commutative. We know that we can multiply in any order. So whether you say A times B or B times A, you get the same results. And multiplication distributes over addition. So we know if you take a real value A and multiply it by B plus C grouped together, then that's the same as AB plus AC. And then our multiplicative identity is 1. So the real numbers contain 1, which has the property that 1 times A is A for all numbers in the real numbers. And our multiplicative inverses, which we think of as reciprocals, are A inverse, or what you might think of as 1 over A. So for every element or number A in the real numbers, it has the inverse A inverse, which we indicate by A to the negative 1, such that when we multiply A by its inverse, we get 1 here. And we define division, A divided by B, as A times B inverse. So matrix addition and subtraction has all of the usual properties: closure, associativity, commutativity, zero matrices, and opposites. A zero matrix has zeros in all the entries, but because a matrix can have any dimension, m by n, we could have infinitely many zero matrices, m by n. So you could just write it 0 with the m by n dimensions in the subscript. So like if you had a 0 4 by 5 matrix, you could put 0 and then 4 by 5 in the subscript so that you don't have to write out all of those zeros in a matrix. The opposite of a matrix, for example, Aij matrix, is negative Aij, and that negative distributes inside the matrix. We'll see that in our first example here. And then multiplication of a scalar by a matrix has all of the usual properties: closure, associativity, commutativity, multiplicative identity, using the scalar 1, and distribution. And for distribution, we have two properties here. So the first property is that a constant times a plus b grouped together, that constant scalar multiple distributes through to both matrix A and matrix B. And then the other property is that if we have C plus D scalars grouped together times A, that's the same as if we distributed C through A and D through A and added them up. So let's take a look at examples here. So in the first example, we've got -1 multiplied through by this matrix. And so we can translate that just to a negative sign times the matrix. And then that negative distributes through to each element here inside the matrix, each entry. And so that changes the sign. So every entry in the matrix has its sign changed. So the opposite of the matrix -8, -9 in the top row and 7, -9 in the bottom row is this resultant matrix with +8 and +9 in the top row and -7 and +9 in the bottom row. So the opposite of a matrix is just a sign change for every element inside. In the second example, notice we're taking a matrix and adding to it here its opposite matrix. So you can think about this as matrix Aij, or in this case, we could call it A23. And then this other matrix over here would be -A23 or -Aij. And so when we add them up, we get the 0 matrix resulting. So every matrix has an opposite that we can add to it and create a 0 matrix. The multiplication of matrices is closed, it's associative, and it distributes over matrix addition. The multiplicative identity matrices are square matrices with ones on the diagonal, what we call the main diagonal here, and zeros every place else. And we call this the identity matrix. So if it's a 4x4 matrix, we'd use I with a 4x4 down in the subscript. In general, we'll call it I n by n. And then if A is an m by n matrix, then I is the dimensions of the rows. So if A is, say, a 3x4 matrix, and I would be 3x3, so that we can multiply it through, because remember, the columns of the first matrix have to match the dimension of the rows of the second matrix. And then if you wanted the identity on the other side, that would correspond with the dimensions of the columns of A. So the identity matrix, if you want to do A times an identity matrix to get the same result, would be n by n, where n is the dimension of the columns of A. We can also define exponents for square matrices. It does have to be a square matrix to multiply by itself. And we can use positive integers k for that. So a to the k would just be square matrix A multiplied by itself k times. And you can see why a non-square matrix wouldn't work, because we wouldn't be able to keep multiplying it by itself because the dimensions would mismatch. And then we define a to the 0 as the identity matrix, just in the same way with the real numbers as any number to the 0 exponent we define as 1. Multiplication of matrices is actually not commutative in general, though, because we know if you multiply a matrix on the left or the right, you might get different results depending on the dimensions you're working with. And many matrices do not have multiplicative inverses. So a singular matrix is the name for that. A singular matrix is a matrix that is not invertible. And later on in the semester, we will see that a matrix is singular if and only if its determinant is 0. So there's a relationship there. And we will study later on how to calculate the determinant and check if a matrix is singular or not. And then division of matrices is undefined. So let's take a look at some examples that are going to verify these properties for us. So in this first example, I've got an identity matrix. This is I 2 by 2. And I'm going to multiply it by a matrix here that is 2 by 3. So I'll call this A 2 by 3. And so my results here remain unchanged. You can check by multiplying by hand. The 1, 0 row is going to reproduce the whole same first row as A, and the 0, 1 second row is going to reproduce the whole second row as A. So when we multiply these, we get just the same results. All right. Now, if we want to do a identity matrix multiplied by A on the right side, A is still this 2 by 3 matrix. So since A has 3 columns, we have to use the 3 by 3 identity matrix. So which identity matrix you use if your matrix is not square depends on which side you're wanting to multiply by. So you can see multiplying the first row of A by column 1, 0, 0 is going to reproduce that first row of A for us, and so on. So we get all the same results, same first column, same first rows. All right, in the next set of examples, notice that we've got a 4 by 4 matrix here. I'll call it, or sorry, 2 by 2, a B 2 by 2, and I'll call this A 2 by 3 because it's the same matrix again. And we're going to see what happens if we multiply B times A. Since B is a 2 by 2 matrix and A is a 2 by 3 matrix, the number of columns of B matches the number of rows of A, so we can multiply. So we know 8 times 5 is 40, and 9 times 6 is 36, if I did my math there right. So when we add that up, we get, oh, sorry, 9 times 6 is 54. It wasn't adding right in my head, no wonder. So we get 94 here. And then this is why we like to outsource this to Simpy to do our calculations for us. And then 8 times negative 9 is going to be negative 72, and 9 times negative 5 is a negative 45. So we get negative 117 there when we tally it up. And then 8 times negative 2 is negative 18, and 9 times 3 is 27. So that difference should give us an 11 in there. Oh, sorry, 8 times negative 2 is 16. I misspoke. See, again, my technology is much better than trying to do this by hand when we might make lots of errors. Negative 7 times 5 is negative 35, and 9 times 6 is that 54 again. So this works out to be 19 when we sum those up. Negative 7 times negative 9 is positive 63, and 9 times negative 5 is negative 45. So those add up to be the 18 there for us. And then negative 7 times negative 2 is a positive 14, and 9 and 3 is 27. So that gives us a positive 41 here. All right, what about this second multiplication? Can we take A, a 2 by 3 matrix, and multiply it by B, a 2 by 2 matrix? In fact, we can't, because the number of columns of A don't match the number of rows of B. So this product is undefined. So this is why we say that multiplication of matrices is not commutative. All right, and then let's take a look at our last example. So in our last example, we are going to multiply a 2 by 3 matrix by, I guess we'll call this D, a 3 by 2 matrix. So we are going to be able to multiply A times D and D times A over here in the second example, but we're going to see the results are not the same, showing us that multiplication of matrices is not equal. It's not commutative when we multiply in opposite orders. So you can double check my calculations here. A times D gives us a 2 by 2 matrix with the top row that is negative 29 and negative 7. And the bottom row is negative 7 and negative 8. And this is a 2 by 2 matrix because we are taking in our resultant matrix the rows of A and the columns of D. Now, if we multiply D times A, we're going to be taking the rows of D dimension and the columns of A dimension. So we're going to get a 3 by 3 matrix here as our result. And so that calculation works out to be -5, 9, 2. And you're welcome to pause and go through the calculations by hand on paper and check to make sure they match my work here. And then the second row of 16, -23, -1. And in the third row, 9, -22, and -9. And you can also run through these calculations in Simpy if you want to verify them as well. Okay, so now we have a theorem. So theorem 2.5 tells us that for a linear system, or for a system of linear equations, exactly one of the following is true. So they're not all true, just one for each system. The system either has no solution, which we call an inconsistent or a singular system. The system has exactly one solution, which we call a consistent or a non-singular system. Or the system has infinitely many solutions, which we also call consistent, but we describe that as a singular system. And so remember that we use a free parameter or free variable, usually t or s, to represent the solution set. So let's do a proof using now what we know about matrix operations. All right, so given a system of linear equations, we've got AX equals B, and I can write X and B as vectors since they're column matrices here. All right, so exactly one of the following is true. The system has no solution, the system has exactly one solution, or the system has at least two solutions, which we call X1 and X2. So we can say if the system has two solutions, then A times X1 equals B, and A times X2 equals B. So then we can say, okay, well, AX1 minus AX2, we know from matrix properties, we can pull that out, and that is A times X1 minus X2. So we know those are equal. And then we also know, well, AX1 is B and AX2 is B. So this is also B minus B, which equals 0. All right, so we're going to let some other variable X sub H equal this back here, the X1 minus X2 difference. All right, so X sub H is a non-zero solution to this homogeneous equation. I call this a homogeneous equation because the solution is 0. If it was equal to some other value, we could call it non-homogeneous. All right, so then let's imagine any scalar value t. X1, that first solution, plus t times x sub h is also going to be a solution. Of ax equals b. And that is since a times the x1 plus txh, we can distribute through and get matrix A times x1 plus t times a x sub h using our matrix properties. And so that's going to be b plus t times 0, because a times x sub h is 0. And so that's just b. All right, so we have shown here that if the system has two solutions and the system has infinitely many solutions. All right, the other two parts of the theorem were that the system could alternately have one solution. So there's nothing to prove there, because if you've got one solution, there's no contradiction with the other two properties. And then the other statement that might be true is that if the system could have no solution. So again, if the system has no solution, then we also have nothing to prove, because that doesn't contradict with any of the properties. So by proving that if the system has two or more solutions, then it has infinitely many solutions, we have proven theorem 2.5.